Good evening, my YouTube viewers. Crystal here. I'm here this evening because I wanted to give you another video. I'm giving you a video about sunspots today. I hope the quality of the video is better than the quality in the past, because in the past I accidentally had the system speaker on, so it was picking up all the noise from the computer, but I've turned off the system speaker, so hopefully you won't be getting any noise from the computer. Hopefully the sound quality will be better, although I do acknowledge that the quality of this little Chromebook, the sound quality isn't fantastic, but we'll just have to make do. So I'm on my GitHub account, Tracy Renee, under miscellaneous TS, sunspots, stat models, and profit, if you want to follow along with me. So first thing we'll do is we'll discuss the problem statement of this, and the problem statement is this data set describes a monthly count of the number of observed sunspots for just over 230 years, 1749 to 1983. The units are a count, and there are 2,820 observations. The source of the data set is credited to Andrews and Hertzberg, 1985. So the first thing we need to do is load some of the libraries that we will need to perform most of the task. And then the next thing we need to do is we need to load the data set. So I've got the data set off of Jason Brownlee's GitHub account. I was looking on Jason Brownlee's website. I think it's called Master Machine Learning or something close to that. And so that's where I got his his data set. So, but I did actually load the program on my site. So you'll have to look on two GitHub accounts, Jason Brownlee's GitHub account to get the data set, and my GitHub account to get the program. So the data set is broken down into month. It's got two columns, an index column, which is month, and then sunspots. We did a train info. So you've got the first column, which is month, which is an object, and then the second column is sunspots. I checked to see if there were any null values, and there were not any null values. So we didn't have to impute any null values. So what we've done here is we've got a little formula here, so you can look at the sunspot data, and it's plotted on a graph. So you can see that from 1749 to 1983, and you can see that it's done cyclically. And then we've just got a different type of graph because all of the values were positive. We were able to show the graph on the negative side of the graph as well. So this is a two-side view of the graph, so you can get a better look at it. And you can see that these sunspots are cyclic, that they form a pattern. So what we wanted to do is we wanted to do another graph, because I guess I just like graphs. So I put as many graphs in as I could find. We got another graph of the sunspot data, and you can see that it's cyclic. And so we've got another graph. This is just a different way of looking at the sunspot data, but you can see again that it's cyclic. So now what we've done is we've created another column called year, where year equals train, month, as type string, train year equals year string 4. So basically what they're doing is they're only taking the first 4 characters of that string. And so now what we've done is we've used a group by command, so you can group the sunspots into years, and you can see which years you had sunspots. And again, we can see that there is very much a cyclic pattern here. So now we've created another variable called month. Month equals train month as type string. Train month num equals month string 5:train. So now what we've done is we're not looking at the first 5 characters, and then we're just taking the last 2 characters or the last 4 characters. And so we've got a different now we've got a different column called month num, and it's just a number. It's not written out in string format. So we got another graph, so you can see how many sunspots you had each month if you want to see that. Now what we've done is we've made a new variable called temp equals train group by year, month num, sunspots mean, and then we've plotted that. So now you can see the mean sunspots of the year and the month. So the next thing we've done is we've time-stamped our index. So train timestamp equals PD to date time, train month, format equals year month. So now we've got a new column called timestamp. Train index equals train timestamp. So now the index is actually the timestamp. Monthly equals train, resample and mean train. So what they've done is they've resampled it by the month. So now we've got another graph that says monthly sunspots, and you can plot it. So this is your monthly sunspot, so you can see that it's cyclic. Now what we're doing is we're defining our training and our validation dates. So I just had to pick a date. So I decided that the training dates are going to be January 1st, 1749 to December 31st, 1949. So that was 200 years. And then the validation date is going to be January 1st, 1950 to December 1st, 1983. I suppose I could have made it December 31st. I made a mistake. No, it wasn't a mistake. It was December 1st, 1983. It wasn't a mistake. Because what I did was I had to look on the validation set, and I picked the last date of the validation set. So the last time that it was sampled was December 1st, 1983. But I guess if I had put December 31st, 1983, I don't guess it would have made that much of a difference. But I just looked on the data frame, and I used the date that was on the data frame. So we've got the train and we've got the valid, and it says December 1st, 1983. But if we go over here with the train, again, it says December 1st, 1983. So I didn't make a mistake. I was a little bit worried I'd made a mistake, but I didn't. So now what we're going to do is we're going to plot that. We're going to plot the train and we're going to plot the valid. So you can see that the train is blue and the valid is orange or amber. So now what we're going to do is we're going to take the Nave Approach, and I did study the Nave Approach a little bit, and what I'll have to do is when I do my blog post, I'll have to research this and say what everything means. But Nave Approach, they just take the last value and use that. So here's a plot of the Nave Approach, and you can see that the Nave forecast is in green. So you can see all it is a straight line. So we've calculated our errors, and our RMS is 69.61. We've got a data frame of Y hat, so I showed that. We made a data frame where you can predict the actual against the predicted, and you can see what it is, and you can see that it was all one value of 117.6. The next thing we checked was auto-regression, and that is in your stats models. Let's just check Nave. Nave doesn't appear to be in stats models. I looked it up because I wasn't sure what the difference between Nave and auto-regression was, and it doesn't appear to be in stat models, but I'll look it up some more. And we checked auto-regression, and so I've got a formula out of stat models, and we ran the formula to get your y hat. And so I ran a data frame so you can compare the actual values against the predicted values. And made a graph of it. So again, you can see that when you do the graph of it, it starts out a little bit cyclic, and then it peters out to a straight line. So that's your AR. And our RMS is 61.57. The next thing I'm going to check is our moving average. And again, we put a little formula in there. Get your y-hat. And I put a data frame in there so you can compare the actual values against the predicted values. Plotted it on a graph so you can see that what happens is it starts out at one value, and then it takes pretty much a 90-degree angle, and then it's a constant value after that. And so we check our RMS at 64.06 RMS. Now what we want to do is we want to check auto-regressive moving average. So that's ARMA. So I've got a formula from stat models to get our I put a little data frame in so you can compare the actual values against the predicted values. We graphed it, and you can see that it makes a slope that the values start out high and then they go low. We checked our RMS at 62.92. And now what we're checking is seasonal auto-regressive integrated moving average. That's called SARIMA. So I've got a little formula that I got from stats models to get our y-hat. I plotted a data frame so you can look at the actual values against the predicted values. And we graphed it, and you can see that this figure just goes all the way down. It goes down into negative values, really. So that doesn't look very good to me, does it? Does it look good to you? And we check our RMS, and it's 117.62. So now what we're going to do is we're going to look at simple exponential smoothing. We've got a little formula from stat models to get our y-hat. I put a data frame in there so you can compare the actual values against the predicted values. Again, you can see it's just a straight line. We check the RMS, and it's 75.07 5733. So the next thing we do is we check Holt-Winters exponential smoothing. We've got a little formula that we got out of stat models to get our y-hat. We plotted this, and again, this is just a straight line. Our RMS is 77.79, and I guess chart in there. No, I did put a chart in there. So that's everything for stat models. So now what I decided to do is I decided to go ahead and put Facebook profit in here. So now we're going in Facebook profit. We've left stat models. So we've got some more formulas in here to create our X and Y values. And we create our features and targets. And we've got a data frame that shows you our features and targets. And we use Seaborn to plot graphs. If you really like graphs and you know how to use graphs, but you can see that it's all cyclic. So now what we've done is we've split our date. So our split date is January the 1st, 1950. So S train is before the split date and S val is after the split date. So now you got your S val. You can look at that. So what we had to do is to make this work, we've had to drop several columns. And the reason why is because Facebook profit only wants to see 2 columns. It wants to see the time, which it calls DS, and it wants to see the number, which it calls Y. So in order to make this work, we had to drop a lot of columns. So now SVAL just has the index and the sunspot. And now we have a plot on this. So the train, which is a capital T, is amber, and the val is blue. So what we've done now is we've had to reset our index because, again, Facebook profit doesn't want to see it as an index. They want to see it as a column. So timestamp is going to be a column called DS, and sunspots is going to be a column called Y, and the index is reset. Now you can look at S train. So we can say S train date time equals S train index, and S val date time equals S val index. So now we set up our model and fit it, and we get our S val forecast. It goes all the way over to Y hat. So the next thing that we're going to do is we plot it, and you can see the way that it has been plotted. And then the next thing we're going to do is we're going to plot some more. We're going to do some more plots. So what you can do is you can compare the actual values with what they've plotted. So the mean absolute error is 48, and I think that's different from RMS. But it looks to me like it's a little bit more of a slope than what we got with stat models. So the next thing we do is we put this on a data frame and we compared our actual values against our predicted values. And now what I decided I wanted to do is I wanted to use it on random forest because Jason Brownlee said you can use random forest for time series analysis. So I just wanted to see if that was true. So we set our X and Y values. X is train.index rise.0 reshape -1, -1, and Y is train sunspots values. So we use our chest train split. I split this up for 15% would be the validation set. Now what we do is we check random forest regressor and we fit that in. We got 98% accuracy. And when we predicted on XVAL, we've got a 90% accuracy. We've got an RMS of 14%. So the RMS on random forest is much better than the RMS on stats models. And so we've got a data frame that compares the actual values against the predicted values, so you can look at that and see how close we were. And now what we've done is we plotted a graph, and you can see that the predicted values and actual values are quite close. And that was it for this presentation. So I used stat models, Facebook Fit, so I think that Random Forest scored okay, and Facebook Profit scored okay. And truthfully, if I had to choose, I would choose either Facebook Profit or Random Forest. But the problem is Facebook Profit used a value called MSE, and Random Forest used a value called RMS. So their values are a little bit different. So what you'd have to do is you'd have to use both Random Forest and FB Profit to see which one was best. So this concludes my presentation. I hope you got something out of it, because I've compared 3 different libraries in Python that you can use to conduct a time series analysis, and I'm giving you the code to do that. So if you like my video, please like, subscribe, and share. If you like the work I do and you want to make a donation, I've got my email address to my PayPal account in the description below. I don't have enough subscribers to monetize my channel, so I have to ask for donations. And thank you so much for watching my video, and I look forward to making new videos for you.